Okay, so last lesson we talked about these energy levels, sublevels, and orbitals, right? And also the spin. So just a quick recap. Remember this picture, and we will move on to the next one. Okay. Okay, so we talk about the energy levels, and we will usually represent the energy levels using an integer number, and that's the main quantum shelf. And the number of electrons in each main quantum shelf, that means this good old days shell, is 2n squared, where n is the quantum number. So the inner shell is n equals to 1, n equals to 2, n equals to 3. Okay, and within each energy level, we further divide it into sublevel SPDF. So you can think of one acronym, or you can try to think of something that represents SPDF, so that you can remember it. You can form up a sentence and try to suggest to each other how to help yourself to remember SPDF. And every sublevel consists of orbitals, and orbitals are regions of space whereby there's a high probability for you to locate an electron. And when we say high probability, we are looking at a 95% chance of finding an electron there. And every orbital can hold two electrons of opposite spin. And when we talk about opposite spin, we are talking about something like this. If we use an arrow to represent one electron, if we represent an electron using one half arrow, so opposite spin means something like this in this picture. Okay, whereas this means parallel spin. Okay, parallel spin. So which is wrong. Wrong. Okay, because we want opposite spin. So I understand the last lesson we talked about the shapes of the orbital, so I'm going to slowly reach there, okay? So we talk about orbital numbers, SPDF, and so on. Okay, so let's go on. Okay, so S is spherical in shape, and as the energy level increases from 1s to 2s to 3s, the shape is still the same, but just that the size is clearly bigger, and every s orbital can hold two electrons, and they're spherical in shape, they're non-directional, means you don't have a certain facing. Whereas for the p orbitals, you will see there's a px that lies on the x-axis, py on the y-axis, pz on the z-axis, and altogether they come in a set of three. They come in a set of three. So let's say you only have one electron. Do I need a set of three? Yes, you will still need to have a set of three. You cannot just get one orbital. It has to be a set of three, but only one electron will be filled in because you only have one electron to fill in. Okay, so compare a 2p to a 3p, the size increases, size of the electron clouds increases, okay, and so on. And it's directional. So there's specific direction that is lying or facing. So then we have our D. So the takeaway, if you cannot remember the name, is fine, but at least remember the D orbitals comes in a set of 5. It comes in a set of 5, okay? And so on. So which are the energy levels that can have D orbitals? It will be the third energy level onwards, because as ED, so there's a third sub-level, so the energy level must be the third one also. So understand? So if the energy level is 2, then you have only 2 sub-level. If the energy level is 1, then you can only have 1 sub-level. If the energy level is 4, then you will have SPDF, 4 sub-level. Okay, and then we move on. Okay, let's try to summarize what we have heard just now. So if the principal quantum number is 1, then the number of subshell is 1. And the type of subshell is called S. Wait. And how many orbitals are there in S? One orbital. S is only one square box orbital, right? And how many electrons can you fill in? Every orbital, 2 electrons, so 1 times 2, 2. So what's the total number of electrons in the first shell? 2. Second shell, how many subshell can you have? If it's a second quantum shell, you will have 2. And what's the name of the subshell? We call it S and P. S is made up of one orbital and P is made up of a set of 3. And every orbiter has 2 electrons. So 1 times 2, 2, 3 times 2, 6. In total, the total number of electrons is 8. So the second shell, you can hold 8 electrons. The third quantum number will have 3 subshells, and we give it a name. We call it S, P, and D. So S has 1 orbiter, P comes in a set of 3, D comes in a set of 5. So SPD. 2 electrons in each orbiter, so therefore 2, 6, 10, and we sum it up is 18. So the third shell actually can house 18 electrons. Okay, and so on and so forth. So fourth shell will be called S, P, D, F. S becomes 1, 3, 5, 7. So if you realize, you see that it's a series of odd numbers, 1, 3, 5, 7. Okay, number of electrons will be 2, 6, 10, 14. Add it up, that will be 10, 20, 32. Okay, and that's how you work it out. Okay, so this is how we understand about some electrons and orbitals. So we're going to move on to learn how to put them into the shell. Okay, so we have gone through this. Okay, so sometimes when they ask you to fill in the electrons, they may ask you to draw it into boxes like this. And the name that we use to describe these boxes like this is called arrow in box diagram. So when question says draw arrow in box diagram, you draw this with electrons inside. But if question says draw the orbitals, then you will draw these orbitals, this orbital, spherical, all this. So if they want you to put the electrons inside the orbitals, then they will call it arrow in box diagram. Okay, they don't really call it orbital diagram, they call it arrow in box diagram. Okay, so instead of using a dumbbell shape or a spherical shape, we just use square boxes to represent the electrons so that it's easier to draw. Now you'll find that the relative energy of the orbiter, if you look at this slide, which is very important, look at this slide, and you'll find that it's not the same. You see that 1 has lowest, 2 has higher than 3, 2 has higher than 1, 3 has higher than 2, and so on and so forth. So as the energy level increases, the energy of the orbitals also increases. And if you look at within the same group, within the same quantum shell, so we find that P is higher than S, and then D is higher than P, and so on and so on. Okay, so next thing is that now you will see that it's just a very clear cut. 1 here, 2 here. But when it comes to 3, you start to see that there's some overlap. Some of the 4 went into the 3, right? And that happens because when it goes towards higher energy levels, that starts to see overlapping of the position of the energy. Sorry, what I mean by is overlapping of the energy of the sublevels. So there's some overlapping in the energy of the sublevels as seen in the picture. Now, just to explain to you why. Why is this happening? Why is it that 1 is so nice, clean cut, 2 is a clean cut. When it comes to 3, then suddenly you see some 4 within them. And then when it goes to 4, you will see some 5 within them. It is due to the shells. We go back to our good old days shells. So in the good old days, when we draw shells, we draw it so nicely as though they are evenly spaced. They are evenly spread out. But in reality, they are not. In reality, as the shells goes outwards, they are actually getting closer. Okay, my circle is terrible. Okay, my freehand circle is terrible, but you understand what I'm saying? So as you go further, the gaps between every shell is actually getting smaller. So we call this energy level converging. So the energy levels are getting closer in energy, they are converging, but yet we are fitting in more sublevels. So lesser gap, but more sublevels to go in. So in a way, it will start to overflow and go down into the next region. So that's why you see the 4s over here is like somewhere inside the 3D in a three quantum shell space in a way, right? So this anomaly will start to appear at higher energy level because of energy level converging at high energy. Okay, can you take down first? Okay, so then the thing is, let me clear up the drawing first. So when we are filling the electrons into the orbitals, just like the good old days when we are drawing the shells, we fill the inner shells first, then we fill the outer, and so on, right? Then we move on to the next one, and so on. So the same for orbitals. So when we are filling it with electrons, we will fill the lower energy first. So after we fill out 1s, then we go on to fill the 2s, then the 2p, and then we go according to increasing energy. So we, after that will be 3s, then 3p. But that's the problem here now. The problem is here. Can you see here? All right. The problem is here. So you'll find that I go according to that order and I reach a point whereby I'm seeing 4s before 3D. So just take note when we are filling electrons, we must fill 4s before 3D. Okay, we fill 4s before 3D. And the reason for that is because it's very clear that 4s is lower energy than 3D when it's empty. So when it's empty, you see 4s here, you see 3D here. So 4s is lower in energy than 3D when it's empty. So the idea here is that we have to fill the lower energy orbital first, then we slowly move up. Right? So we have to fill 4s first, then we fill 3D. Okay? And that is when you're feeling. So when it's empty, 4s has lower energy than 3D. However, when 4s is filled with electrons, then it becomes higher energy than 3D. Okay, it's a bit complicated. I repeat, when it's empty, 4s is lower energy than 3D. However, when it's filled, then 4s has a higher energy than 3D. I will show you the thing in a while. Okay, so let me move on first. Okay, so because of the overlapping, it's not only to 4s. You will find that there will be a lot of overlapping, and there's no way for you to remember who comes next because of the overlapping at higher energy level. So there's a way for us to try to know which orbiter is next, which is the next page slides that we are going to go through. Okay, but before we go there over, just remember in this picture, when it's empty, you will, okay, so when just look at this picture and remember, we fill the lowest energy orbital first, and when it's empty, 4s is lower energy than 3D. But once the electrons go into 4s, 4s now become higher energy than 3D, and therefore it will move above 3D. Okay, in terms of this energy level. That means when this diagram, right, when it's filled, then once it's filled, right, 4s will be higher than 3D already. I think I have a picture to show you later on that. All right, so when we fill the electrons, we follow a series of rules. We follow this thing called the Aufbau principle, Pauli exclusion principle, and Hans rule. Now, if you cannot remember who the name is fine, but it'll be good to acknowledge the person who worked so hard to come up with the rules. Okay, but basically what you need to know is the rules. Okay, so Aufbau principle states that when we are filling electrons, we should fill with the lowest energy orbital first, and we follow a certain sequence, and the next one, and the next one, and the next one, and the next one. Because of the overlapping, so sometimes who's the next becomes a little bit unclear. So if you look at this video, it will teach you how to tell which is the next one.
In this video, we are going to learn how to write the electronic configuration for a given element. To do so, it's it is important to get the order of the electron shells correct. How can we do that? First, we must list all the s subshells in an increasing order in a vertical manner like this. For the first electron shell, there is only s subshell. For the second electron shell, there are 2 subshells. So to the right of the 2s subshell, we write 2p subshell, as well as for the rest of the electron shells with p subshell. Similarly, to the right of the 3p subshell, we list the d subshells and finally the f subshells accordingly. Do you know why we stopped listing at the 6d and the 5f subshells? Of course you can continue, but this is not necessary because we have already represented all the subshells occupied by known elements in the periodic table. Now, let's fill in the electrons. Remember that the S subshell can hold a maximum of 2 electrons. P subshell can have 6 electrons, D subshell 10 electrons, and the F subshell can hold up to 14 electrons. When we fill the electron shells, we always start with the one that is the closest to the nucleus, which is 1s. We can use this blue arrow to guide you the correct order of the electron shells to fill in. So
Oh,
after
look at
1s is
how the
filled,
video
we
fills
continue
up
with
the
2s,
electrons.
then 2p, 3s, 3p, 4s, and so on. Now we are ready to fill the electron shells. Let's try with sodium, which has 11 electrons. How do we assign them? Remember, we start with 1s subshell. When it is completely filled, we start to fill up the 2s subshell. The number in superscript refers to the number of electrons that has occupied the subshell. Again, after the 2s subshell, we move on to the 2p subshell, which can take up to 6 electrons. So the last electron will occupy the 3s subshell. The electronic configuration for sodium will be 1s2, 2s2, 2p6, 3s1. Let's practice with another element, vanadium. Vanadium has 23 electrons. Again, we start with 1s subshell, followed by 2s, 2p, 3s, and 3p subshell. At this point, we need to fill the electrons into the 4s before the 3d subshell. This is because the 4s subshell has a lower energy level when it is empty. Now we have filled in 20 electrons, so the remaining 3 electrons.
Okay, so remember at this point, you fill with 4s first, then 3D, because it's lower in energy when it's empty. Okay, so beyond that, now you have already filled like 20, you still have 3 more and see what happens.
Will occupy the 3d subshell. When we write the electronic configuration, it should be arranged in numerical order. That is, the 3d subshell should be written before the 4s subshell. Because of this, we should interchange the 4s and the 3d to give the correct written representation. So the electronic configuration for vanadium is written as 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2.
Okay, so take note that the number of electrons is a superscript. That means it's flying up one. Okay, whereas the quantum shell is a normal number, whereas the 1s2, the 2, and 2p6, the 6 is a superscript. And it is better to follow what the video says, to rearrange according to increasing quantum number. So you see all the 1 lines up, the 2, then line up all the 3, then line up all the 4. That is better for you because you will tend to make less mistakes when you form a cation later. Okay, because for cation, or when the atom loses electrons, we always lose from valence shell. So by rearranging it, it's very clear which is the valence shell, and it's very clear where do we take the electrons from. Now, the mistake always comes from the cation because the students do not rearrange it, and as a result, when they see it, they always see the D as the last one. Like in this case, let me just show you the previous one. We first should rewrite. Yes, this one. So if you don't rewrite, it will appear to you that D is the last. And when you remove electrons, you will take from the D, which is wrong because we always remove from the outermost shell. But if you rearrange it, then it will become very clear. 4 is the last, and you remove from outside in. Okay? So when 4s is filled, its energy level is higher than 3D. So therefore, when you want to remove electron, you will remove from 4s.
In this video, we are going to learn how S and the 3Ds 1s2, 2s2, 2p6, 3s2, 3p6, 3d3, 4s2. By following these two examples, you are now ready to write the electronic configuration for most of the elements given to you.
Okay, so I want to bring you to this. Now, during exam, it's not given. This table is not given. So you must be able to draw it out. You don't draw, you don't know what comes next as a sequence. So 1, then 1. So when you slash it, it looks something like this. 1, then 2, then 2p, 3s, then 3p, 4s, then 3d, 4p, 5s. Can you see 5 comes before 4d? So 4d, 5p, and 6 come before 5d, and come before 4f, and this all. So the sequence has mixed up along as we go higher energy. So therefore, we need to know how to draw this table so that you know which is the orbitals or the sublevels that's coming next. Okay, so 4s has lower energy than 3D before filling, so therefore we will fill 4s first. But once it's filled, it has higher energy, and we arrange in terms of increasing quantum shell. So when we remove from 4s first. All right, now this is another picture. So the previous one shows 1 at the top and then 2 and 3. Because actually it's quite misleading because those at the top should have the highest energy. So therefore, if you do like this, you need to know that you're writing the lowest energy at the top. Okay, so the other picture that I'm going to show you next slide is to show is the correct order, whereby 1 is below and then 2 is higher. So something like this, 1 below 2, and so on. Now, this is the correct order, but it is a little bit harder to do the slashing compared to the other one. Okay, so you see whichever works for you. Okay, so every orbiter can hold 2 electrons and it must be an opposite spin represented like half arrows. So you look at this is called parallel spin, so it's wrong. You look at this, it's opposite spin, so it's correct. Okay, now the next rule is that orbiters of the same subshell must be singular first before pairing. Okay, so if you remember, if they belong to the same subshell, then they have the same energy. And there was a word used to describe the same energy, it's called degenerate. They are degenerate orbiters with same energy. So these orbiters must be filled single first before pairing. So that means I need to fill them one by one first. Then I start to pair them up. Okay, so that means things like these are wrong. Wrong. Understand? Because I must fill single first before pairing. And the reason is because these arrows are representing electrons. And electrons are of the same spin charges. And they repel each other. They repel each other. So they do not actually like to be together. Right. So as much as possible, you put them singly first, then you pair them up because the moment you pair, of course, they'll bring about some electronic repulsion. Okay. And also it must be of the same spin. Okay. So you cannot have one up, one down, one up kind of case like over here. All right. Okay, so the electronic configuration can also be determined by the periodic table. So instead of keep doing 1s2, 2s2, 2p6, sometimes you can do a shortcut and you can work out its electronic configuration. And how? Okay, so this cluster here, group 1 and 2, is what we call the S block element. S block element means that the configuration ends with S. So this is called S1 and this is S2. And this chunk here is called the P block element. So the configuration sure ends with a P, sure ends with a P. So it'll be like P1, P2, P3, P4, P5, P6. So it sure ends in this manner. And then the center one is called the D block element. And then the one below is F block element. So the configuration of an F block element will always ends with F. Now, D is a problem, a little bit of problem here. So usually if we go by in the order of counting, then this will be D1, D2, D3, D4, D5, D6, D7, D8, D9, D10. But there are two, there's an anomaly that doesn't really follow, which is instead of it's a D4 over here, it will be a D5, D5. Okay, instead of a D9 here, it will be a D10, D10. Understand? So it's D1, D2, D3, D5, D5, D6, D7, D8, D10, D10. Okay, that is the anomaly. I'll explain to you why is it so. But now let's look at this. The focus is to use the periodic table and come up with the configuration. How? Let's look at iodine. What do we see? Is P5 and is in which period? 5. So that means whatever was its configuration, whatever its configuration is, the front part is going to be the same. And it will end with 5p5. So whatever orbitals that came before 5p5 must be there. It must be there. So it must have 1s2, it must have 2s, 2p, it must have 3s, 3p, 3d, it must have 4s, 4p, 4d, 4f, and so on. So it must have all these and then 5s and 5p. So the idea is whatever before that will all be present. Okay, so you can get the configuration very fast. So remember this was 5p5. Sometimes what people do is that they go back upwards one step, and look at the nearest noble gas. One step up to the nearest noble gas, and you find that it's Kr. Kr is in the row of number 4. So after Kr is the row of number 4, the next row is the 5. So the Kr already represent the chunk in front, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s1, 4s2, 4s, 4p6, 4d10, 4g 14 or something like that. You already have the whole chunk there. So what is left for you is the next period, the next row, which is the 5 to write in. That's it. So you will write 5s2, 5p5. 5s2, 5p5. And that will be the configuration. So it will be 5s2, 5p5, and plus a kr. Okay, so I show you one more example how to read. Last one. So look at the periodic table, just anyhow pick a place. Let's say I'm going to practice one. I want to know what's the configuration of this. Very simple. Look, is P1 and is 4P1. So whatever in front before 4P1 must be present. So it'll be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. Then all the 1 and 2 and the 3 has appeared, right? So now 4, So 4s2, 4p1. We stop here. Whatever before must be there. So if you use the condense, then the previous noble gas is argon. Then you will write it as argon, bracket. So argon has all the 3. So you need to put in the 4. 4s2, 4p1. Now, during exam, we do not write this. This is called condensed electronic configuration. Okay, we don't really write condensed electronic configuration. We will usually write the full electronic configuration. So what is full electronic configuration? Full electronic configuration is this. We will not write the condensed, but usually we write the full. Okay? Okay, so I'm going to show you how we fill up. So you look at iron, I fill the 1s first because lowest energy, then fill 2, then fill the See, can you see the previous animation? I feel single first, then I start pairing. I feel single first, then I start pairing. And then the tree gets filled up, and then we fill 4S first, then we fill 3D. So remember, when it's empty, 4S is lower energy than 3D, so we fill 4S first. But now, after filling electrons inside, what will happen? After I put electrons inside already, before it was empty, so 4S lower energy. But the moment electrons are inside, then 4S will have higher energy than 3D. So understand? So when we lose electrons, we always lose from the highest energy orbital first. So we lose from 4S first. Okay. So look at the question. If they say draw, usually we'll be drawing arrow in box diagram like this. So if you look at arrow in box diagram, if you draw in a vertical format, 1 has to be below, 2, then 3, then 4. But if you draw it on a horizontal format, because there's no space to go high up, you just draw in a single line, then it doesn't matter, but you will need to label. So what do I mean by single line? That means you will be drawing like that, 1S2, 2S2, so something like this in my picture here. So you draw it all in a line. So there's 1S2, 2S2, 2P6. So you take note of if you are doing something like this, then you have to make sure, wait a minute, then you have to make sure you label. If you don't label, then nobody knows what you are drawing. So you need to label the orbitals. Okay? Okay, I will do one more, which is the iron, and we will stop there. Okay, and let's look at cations. Now, listen, now this is where it will go wrong. You must listen. So, when the question gives you a cation, you are not supposed to do mathematics calculation and do a subtraction. So, you are not supposed to take 26 minus 3. So, madam, 23. And you start to fill 23 electrons from 1s2, 2s2, 2p6. You will be sure wrong. Wrong. So for cations, what do you do is that you will draw an atom. You will draw an atom and take an eraser and erase the electrons after you have drawn. Understand? You will draw the atom first, and then this question over here says remove 3 electrons because it's Fe3 plus. Then you take your eraser and then you remove the 3 electrons. Now, look, I'm erasing the electron. So now the question is, I've erased the 3 electrons. My question is, do I leave the 4s empty box here and leave it there in my drawing? No, you remove it. You take it off. The business is empty, what? Right? So your configuration will be like that. You should not have the 4S there if you ask me because it's empty. Okay, so I repeat for cations. Okay, this is 1,000,000 times. For cations, you will still draw atom first and you take an eraser and erase the electrons. Okay, do not be smart, Alex, and then go and do subtraction and take 26 minus 3 and say, oh, madam, 23, I will feel 23 starting from 1s2, blah, blah, blah. You will be sure wrong. Okay, because you will end up having a 4s behind. You are supposed to lose 4s first. Okay, so just follow what I tell you. Do not do a subtraction and fill. You should do an atom and clean off. And that's for cations. Anions, not that much issue. Okay, so remember, do not take 20. Do not do this, do not do this, do not take 26 minus 3 and start feeling. It will be, tendency is you will make a mistake because you will not lose 4s first. Okay, so when the question says draw the arrow inbox diagram, you draw me this picture with labels to allow me to understand which is what orbital. If they say write the full electronic configuration, it will be this black rows of numbers below. Okay, so, and if they say condensed electronic configuration, that means you use the previous noble gas to represent a big chunk, then add on whatever is missing. Okay, so I don't think I want to complete this lesson today because it will be, there's a need to touch up, I think, the remaining of the anomalies. So we will not be covering the anomalies here, but we will cover the anomalies when we are back to class. So after the anomalies, let me see how many I have. Yeah, not much slides left already. Okay, so I will stop here. We will not look at the chromium and copper anomaly. We'll just look at the cation ions.